Today we're going to get started on Chapter 6. Chapter 6 deals almost exclusively with the different types of lines that we can draw within triangles. So the main topic through the vast majority of this chapter will be continuing to deal with triangles just as we did in the previous chapter. But what we're going to be looking at are the lines that we can draw within and sometimes outside of triangles. So all kinds of things we're going to be doing, and so it's going to be really important to take decent notes this chapter so that you can distinguish between the different types of lines. Just as a couple of examples, we're going to be looking at lines that are called angle bisectors. These are going to be lines that bisect an angle. So that might be a line that cuts an angle into two equal parts. We might be looking at what's called an altitude, which is a line drawn from a vertex perpendicular to a side of the triangle. And we have all kinds of different options that we're going to be looking at throughout the chapter. Okay? So take good notes so you can distinguish between them. Pretty much every type of line that we can draw has one or two decent theorems that go along with it. So again, take good notes and write down at least one numerical example for every one of the theorems that we go through as we move through this chapter. Okay? So section 1 here in chapter 6 is going to deal with a type of line that we're going to draw inside of a triangle called a perpendicular bisector. Now, we've seen these before. We've actually drawn these before. I've had you draw your own using a compass and straight edge. And obviously on my iPad, I can't demonstrate the construction again, but the idea was that if we have a line segment, so if we have a segment AB, and you draw the perpendicular bisector, we're going to draw a line then that does two things. Okay, so we're going to draw a line that does two things. Number one, we're going to draw a line that's perpendicular to the segment that we started with. And number two, we're going to draw a line that bisects or cuts into two equal parts the segment that we started with. Okay, so it's going to do two things, perpendicular and bisect. Alrighty? Now, the theorem that goes along with perpendicular bisectors when we're talking about a triangle, all right, then are guided by this theorem. It's called, big surprise, perpendicular bisector triangle theorem. So now we're putting these perpendicular bisectors into a triangle. All right, and it simply goes like this. You'll see how the triangles get formed after a little bit. But it goes like this. A point lies on the perpendicular segment if and only if the point is equidistant from the endpoints. Right? I'll just slide that up a little bit so you can still see it. And then I'm just going to draw you a picture of what's going on. We start with the segment. We're going to draw the perpendicular bisector. So we're going to draw the perpendicular bisector. Right? So again, that means both perpendicular and cuts it into two equal parts, right? And then if we pick any point on that line, so we pick this point, or we pick this point, or we pick this point, right? And we consider the distances to the endpoints, so the distances to these endpoints, or the distances, the distances, let's see, we can do this one. Come on, this darn thing. iPad's acting up. There we go, that should work. These distances, or no, let me try the green one again. Or we consider these distances. Those distances are always going to be equal. So those would be the same, these would be the same, or these two would be the same. So you pick any point on that line, and it's going to be equidistant from the endpoints. And of course, now you can see where the triangles get formed. All right. So that's the theorem. That's the theorem that we are going to use with perpendicular bisectors. And please notice, because it's an if and only if, please notice because it's an if and only if, this works in both directions, right? So if the point lies on the perpendicular bisector, then it's equidistant from the endpoints, or backwards. If any point on that line is equidistant from the endpoints, then it's the perpendicular bisector. Okay, it works in both directions, works in both directions. Okay, so first some numerical problems, and like always, feel free to pause the video if you need to jot some things down or catch up to where I am. But some numerical problems then. So if I draw the bisector, or sorry, if I draw the segment vertically this time, and then I draw so I draw a line that is the perpendicular bisector of the segment that I started with. Then any point on that line, like I'm going to choose this one right here and call it C, then the distance from A to C and the distance from B to C have to be the same. So if I were to give you a numerical problem and tell you this distance is 27, and then ask the question, can you find the length of BC? The answer is sure, because that distance has to be exactly the same. So this distance would also have to be 27, because the theorem says those two distances have to be the same. Okay? The theorem also works essentially in the other direction. So here's just another example. So if I give you, let me get this, here's an example. Let me switch to black like I normally would. So if I have a segment going this way, this time, P to R, and then I draw a line, excuse me, and I pick a point on that line like this one right here. I'll just call it Q for the heck of it. And I tell you that those two distances are the same. Let's pretend that this distance is 13 and that distance is 13. If these two distances are equal, then the line has to be the perpendicular bisector of the original segment. So as an example, if I told you this length was 7, then a question we could ask you on a test, I need to put in another letter there, sorry, I forgot. So I'll put in point S right here, I forgot about that. Then I could ask you for the length of RS, and of course, those two distances are gonna have to be the same, so that distance also would be 7. Okay? We could make our numerical problems a little bit tougher. So we could make these a little more difficult. So let me give you an example. Slightly, not much, but slightly more difficult. I give you a segment, G, E, and then I draw a line. I pick a point on that line that I'm going to choose to call F. And, excuse me, if I tell you that FH, if that is both perpendicular and a bisector of the segment that we started with, and I connect F to E and F to G, right, do that connection. But this time I tell you this side is 2x and this side is 3x minus 8. Question, could you then tell me the value of x? Could you tell me the length of FE? And could you tell me the length of FG? So could you answer 3 questions in that situation? Sure. It's not much more difficult, it's just a little bit more work. The idea again, if we're starting with a segment and then we draw a perpendicular bisector to it, that means then that the distance from any point like f to the endpoints are going to be equal, which allows us to then say that 2x has to be equal to 3x minus 8. Those two distances have to be the same. And of course, you guys know enough that you can find the value for x. I'm going to choose to move the 3x to the left-hand side by subtraction and divide both sides by -1. So x is going to be equal to 8. And if x is equal to 8, then FE is going to be 2 times 8, or 16. And FG is going to be 3 times 8 minus 8. So that would be 24 minus 8, or also 16. Okay, so you could answer a 3-part question without much problem, without much issue. Okay, all right. Again, the idea, if you pick any point on that perpendicular bisector, the distances are equal. So we can make the problems look a little more confusing doing something like the following. Again, starting you guys off with a segment, drawing in the perpendicular bisector line. So if this is both perpendicular and a bisector, then we pick any point. So if I pick one on this side, this distance to an endpoint and this distance to an endpoint are the same. So if I were to tell you that this side is 6x plus 11, and this one's 11x minus 9, find the value of x. And that's fine, it's just what we did on the previous problem. But we can make it look a little more confusing by also picking a point on the other side maybe. But the idea is the same, because it says if you pick any point on the perpendicular bisector, the distances are the same. So the distance from the purple point to the endpoints are also going to be equal. So I can give you expressions here then for these distances, 3y minus 15 and y plus 11, and then also ask you to find not only x, but I can ask you to find y as well. Obviously not much more difficult, but the picture just ends up looking a little more confusing. The idea is pretty simple though. The two green segments have to be equal, so therefore you get to say 6x plus 11 is equal to 11x minus 9. The two purple segments have to be equal, so you can say 3y minus 15 is equal to y plus 11. And of course, just simply solve each of the equations. So I'll move the variables to the right, numbers to the left, and divide by 5. So the value for x that makes this true is 4. And then to solve for y, move the variables one direction, I'll go left, numbers the other way. And divide both sides by 2, so y is going to be equal to 13. Okay? So hopefully that's not going to be too bad. Hopefully that won't be too bad for everybody. Okay? Alrighty. We can do proofs with 2-column proofs, I should say. We can do 2-column proofs with perpendicular bisectors. So let me give you an example. Here's going to be a relatively easy one. This will be relatively simple. That's not a very good picture. I'm going to try that again, sorry. In fact, I'll just use my triangle tool to get a better picture in here. Yeah, that'll work just fine. And then I've got to add a couple other lines in here. I'll try to freehand these. And then pick a point. All right, and then the letters I chose, M, P, O, R, where all those come together, and then N at the top. Okay, so let's do a 2-column proof. And what I'm going to tell you is that NP is the perpendicular bisector of MO. And what I'm going to have you help me prove is that triangle NMR is congruent to triangle NOR. And that's a little messy, so I'm going to write that nicer so it's easier to see. That last one's supposed to be NOR. There we go. Okay, and this is a real easy one. This one won't take long at all. But just kind of get you a feel for how it might work in some of our problems. Okay, so like always, we'll start with the given information. So NP, perpendicular bisector of MO. Okay, so that's given. But now we just have a theorem that says if we have a perpendicular bisector, any point on the bisector is equidistant from the endpoints. So what you need to do is you need to think of MO as being the original segment, and then NP is the perpendicular bisector of that. So any point on that bisector, so we're going to work with R and we're going to work with N. The theorem says that any point is equidistant from the endpoints. So what we can then say is that the distance from R to M and the distance from R to O are equal using the perpendicular bisector theorem. And if I use some tick marks here, that means that this length and this length are the same. And if you look at the triangles that we're trying to prove are congruent, NMR, NOR, what that then gives us is a side of each triangle. Okay? N is also a point on the perpendicular bisector. So therefore the distance from N to M and the distance from N to O are going to be equal using the exact same theorem. Okay? So therefore N to M and N to O are equal. And once again, if you carefully look at the two triangles we're trying to prove congruent, what we know then is that we have a second side. So far we have two S's. So to prove the triangles are congruent, we either need another S or we need an A. Okay, and what can we get? Well, the two triangles have a shared side. So NR in the left triangle is going to be equal to NR in the right triangle. This shared side is going to be equal in each. Of course, anything is equal to itself using the reflexive property. And what that gives us then, obviously, is a third side of each triangle. So therefore, if we have SSS, we can prove that the two triangles NMR and NOR are congruent to each other. And the reason is off in the margin there, SSS. And that's what we're trying to prove. Okay. Alrighty. All right, and finally, one last thing that I just need you to jot down in your notebook, but we're not going to I can't really do much with it on the iPad. I'm going to have to show you how to work with this in person. All right, it's a second theorem, and it's going to sound confusing at first, but if you guys just don't worry about it too much, if you try not to worry about this too much until I get back, but this one's called the concurrency of perpendicular bisectors theorem. All right, and let me give you the theorem first, and then you'll see what the word concurrency means. All right, the theorem goes like this. The three perpendicular bisectors of any triangle intersect at a point, and you need to include some parentheses there because we're going to give that point a name. Intersect at a point that is equidistant from each vertex. Okay, and so let me draw you just any old triangle. So, gosh, I gotta do better. So I'm just trying to draw just any old triangle. Okay, so if this triangle we call ABC. And what we're going to do now is we're going to draw the 3 perpendicular bisectors of each side. And I'm going to try just freehand. I'll show you how to do this with a compass and a straight edge. It's going to be pretty tough, but I'll show you how. What we're going to do, and I'll choose some different colors here, is we're going to draw the perpendicular bisector of each side. So I'm going to start with the bottom, AC, and I'm just kind of trying to eyeball a point that would be the midpoint. And then I'm going to try to draw it so that it would be perpendicular. So just kind of doing it by hand or by eye right now. But the best I can, that would be the perpendicular bisector of AC. Then we do the same thing for side AB. Trying to pick the point that would be halfway between, midpoint. And then we have to draw a line perpendicular, and again, I'm just trying to eyeball this, so let me see how I can do. Nope, that's lousy. It's got to be more this way. Yeah, that's better. That would be both perpendicular and bisect that side. And then finally, let me switch to purple or something, and we'll do the same thing for BC. So we pick the midpoint, so that length and that length are equal, and if we draw the perpendicular to the side, okay, that would be the perpendicular bisector. And what the theorem says is that these 3 perpendicular bisectors will always intersect at one point. The theorem actually says a point, but that implies one point. Okay? That point has a funny name. It's called the circumcenter of the triangle. So it's kind of the prefix for circumference. So circum, C-I-R-C-U-M, and then the word center. So circumcenter. And what the theorem says is the distance from each vertex to the circumcenter is going to be equal. So that's what the word equidistant means. Those distances are going to be equal. So if I pick a different color, something I haven't yet used, let me pick green, I guess. So from the circumcenter to A, I forgot to hit the wrong button. The distance from the circumcenter to A is going to be the same as the circumcenter to B, and that's going to be the same as the circumcenter to C. So all of these green distances are going to be the same. So the result of the theorem for my picture, if we call this circumcenter point D, what we're going to say then is that BD is equal to CD is equal to AD. All of those distances from the circumcenter to the vertices, the corners, the angles, are going to be equal. Okay? So there's the second theorem for perpendicular bisectors. Again, I told you at the beginning, for the vast majority of these, there's going to be 2 theorems that go along with each type of line. Now, when I get back on Monday or Tuesday, well, next week, let's just say in general, we're actually going to take some time and draw this out. All right, it's going to be kind of a tough one, but it's actually kind of fun to actually see that it really does work. They all intersect at the same point. Okay? All right, so that's it for the first half of 6.1. I'm going to stop this video because it's getting really long. And then tomorrow I'm going to send you the video for the second half of section 6.1. So you can watch and listen to that video, take notes, and then you should be ready to work on the vast majority of the assignment. Okay? So I hope you're having a good day, and we'll see you on Monday.